So the first thing we're going to talk about is, again, this is the chemical bonding practice worksheet. It's at the very top of the page underneath the arrow. And so I want to go through and I want to be able to answer some of these questions. So hopefully you can answer these questions by now without really having to put a whole lot of thought and effort into it. So number one, how are ionic bonds and covalent bonds different? Well, the way you can describe them actually determines their differences. So, okay? So I want you to write this. So ionic bonds. Okay? Matter of fact, I'm actually going to get off this page because it'll go a little bit faster whenever I write on this. So ionic bonds. So what happens to electrons in ionic bonds? Okay? So electrons are transferred. Transferred 1R or 2R? 100% sure? Well, we're going to leave it like that. Electrons are transferred. Now, we got to add a little bit more to it. So electrons are transferred. Yes, sir. Is it 2? Well, transferred. And now I'm going to add something. I want to see if you can kind of help me fill this in. Electrons are transferred to produce blank and blank. Whenever an electron moves, we create things. You've got it partially right. He said ions, but I need 2 blanks. Very good. So this is what needs to go in here. Cations and anions. Matter of fact, let me ask this question out loud. Brennan, which one of the 2 is positive? Very good. Okay. Jamila, which one of the 2 is negative? Anions. Robert, which one of the 2 gains the electron? How do you know that? Perfect. That's the exact answer. It's negative because it gains the electrons. So that's what's going on in an ionic bond. Okay. Now, so the second one is covalent. Okay. So how are electrons treated in a covalent bond? Very good. Electrons are shared and I'm not a pirate. And are shared. Electrons are shared, and I don't mean an and here. Nope, there's one more. That's close. But what makes them that way, Ryan? Okay, very good. So it's either going to be equally or unequally. Now, I want to add a little word above or below this to finish this out to give us a good thought. Now, Ryan, you said it. What were the 2 words you said? Okay, Baker, which one of those 2 is polar? Very good. Okay. And here's the part that students always mess up on. What's the other one, Bailey? Nonpolar. When I say people wants to match the negative prefixes, what do I mean by negative prefixes? Non and un. People always want to put those 2 together because they kind of are those negative things. But it's opposite. And again, I can't do anything else other than to stress, pay attention to the details. So if it's shared equally, it's nonpolar. If it's shared unequally, it's polar. If you want to add this, if you've got room, you are more than welcome to. So if this electron were shared equally, how would this electron be, how would it look? Okay? It's going to be shared equally back and forth. But what happens whenever we have H bonded with something like F? Okay? It's going to be more, sorry about the noise. It's going to be like that. Okay? That's going to create that unequal sharing. Okay? Lauren, I've asked this 3 days in a row now. Which side, the H or the F, would be negative? Come on. Thank you. Why? Perfect. It's going to gain the electron. So we have those partial positives and partial negative, which creates the polar aspect of it. So if you can understand the basics of this, everything else should kind of go a long ways. So describe the relationship between the length of a bond and the strength of a bond. So don't say closer. Talk about length. Oh, go ahead. Okay. Come here. The shorter the distance, the stronger the bond. That's all you got to write. You can say the shorter the distance, the stronger the bond. What's the opposite of that, Blaze? Okay. Are you writing that in? Okay. So, the shorter the distance, the stronger the bond. Now, I'm going to kind of make an extension upon this. Let's just pretend we're talking about single bonds. What happens when you start adding multiple bonds to it? Every time you add a bond, what happens to the distance? It gets closer, and what happens to the difficulty? It gets harder and harder. So I used that example with Brett. So every time we got a little bit closer, we got a little bit harder to break apart. So that's the same thing there. Now, identify the types of bonds found in the following molecules. I'm going to be honest with you. I hate this word because this is not true. When you see the word molecule, what do you think? Covalent. These are not all covalent bonds. Okay? So really, the word molecules needs to be changed to compounds. Now, this is a really dumb question that I'm going to ask, but I just feel like I need to ask it. Why is it compounds and not atoms? More than one atom. Very good. I just want to make sure that we're clear on that, okay? So, the easiest way to do this is to split the different things that are present. So, I've got chlorine and carbon bonded together, right? So, here's my first question. Is carbon a metal or a nonmetal? It is a nonmetal. Is chlorine a metal or a nonmetal? A nonmetal. So, what type of bond would that create? It's going to be a covalent. Very good. Okay, it's got to be covalent. When you have a nonmetal and a nonmetal, it's covalent. Now, let's look at the second one. When you look at, when you split Li and O, lithium, metal or nonmetal? Metal, oxygen, nonmetal. So what type of bond would it be? Ionic. Very good. Now, you told me just a few seconds ago, when you see the word molecule, you think what bond? Covalent. What do we call those things that have ionic bonds? Crystals. Very good. Crystals, ionic crystals. See if you can do C, D, E, and F. Be very careful with F and D. You did an entire sheet on this that looked just like this. You did 26 of these. Anybody not get this sheet? You tell me. Was that wasn't for a grade, was it? No. That wasn't for a grade. Okay. Count how many you need, pass them back, and then pass them over. What's wrong, Lauren? You sure? Ask. Okay. Yeah, Massimo, what's SO4? All right, so Natalie, let's look at C. Nitrogen, metal or non-metal? Natalie and Natalie only. Non-metal. Natalie, fluorine, metal or non-metal? Non-metal. So what type of bonds you got? Covalent. Very good. Now, I want to go ahead and pause and take this moment because we just talked about the two different types of covalent bonds. And what two different types are there, Emma Rizzi? Two different types of covalent bonds. Emma Rizzi and Emma Rizzi only. The two types of covalent bonds. Look back at number 1. Come on now. Ryan, help her out. Polar or non-polar? The only way that you know if this molecule is polar or non-polar is by drawing it and drawing it only, which we will get to in a little bit. So just hold off on being able to label it that, okay? All right, now, Maya, we've got something strange going on in D. What is calcium? A metal. What is sulfur? Non. And what is oxygen? A non. But what do you notice? Massimo, what is SO4? It's sulfate, Massimo. So since we have a metal and a polyatomic, what kind of bond do we have? Both. Very good. Very good. I'm glad you put that. Okay. All right. Jesus, sulfur, metal or non-metal? This is E. Try again. Non-metal. Why is it a non-metal? What side of that stair-step line is it on? Right side. Right side is always non-metals, right? Okay. What about oxygen? What is it? Non-metal. So you got two non-metals. So what you got? Very good. Covalent. Sharon. The last one. What's magnesium? Metal. What's oxygen? Non-metal. And hydrogen is also a non-metal. So what type of bond is this? Both. Very good. Now, all I need is a hand, please. Hand and hand only. How many of you know what OH is, what polyatomic that is? Don't say it out loud. How many of you know what polyatomic it is? This is why we're doing it again on Monday. Gage, what is it? Hydroxide. OH minus was hydroxide. Okay? So again, that's what we're going to talk about this. Now, let's go down to 4. Does anyone remember the definition of electronegativity? Somebody besides Tristan. It's exactly right. And it's because you're short. What is it, Brett? Here's the part where everyone always stops. But there's an extension. A lot of you can remember, some of you remember this, the ability of an atom to attract an electron, but here's the key part. That's the key. Okay? So, yes, electronegativity is all well and good when you say it's the ability of it to take an electron. That's awesome. But who's the most electronegative? Fluorine, okay? So it has a very strong ability to take an electron. But is it going to take an electron from itself? No, that makes absolutely no sense. So it's got to take it from someone else, but it can't just take it from someone else and run away with it, right? Remember as a kid you took someone's stuff and just run off and made them chase you? It doesn't work that way. When they take or share electrons, what has to happen with those two atoms? They bond. So that's the key part that people always leave out. It's not a take and a give. It's not a take and give thing. Yes, electrons are transferred, but they always end up creating some sort of bond. And so that's what electronegativity is to measure of. The ability of an atom to attract. And I always misspell attract. I have a problem. Attract an electron from another atom in a bond. Okay? So here's what we need to do. A few of these, okay? The first thing I want you to do, so this, determine if the bond between atoms in each example below is nonpolar, polar, or ionic. At least, your goal, and I want you to do all of these, A through H, at least label it C or I. At least get it that far. If you label it C, make an attempt to label it polar or nonpolar based on your knowledge, okay? Go ahead and do that for just a few minutes. Do A through H. At least get I and C right. And then once you have a C, see if you can determine if it's polar or nonpolar. Okay. So, Blaze, starting with you. H2. Shh, stay with me. Covalent or ionic first? Covalent. And again, we're just going to do the covalent ionic part first. All right, Tristan, PCl, covalent or ionic? Covalent. Ashwini, F2. Covalent. Romy, NABR. Ionic. Romy, how did you know it was ionic? Very good. That's right. It's a metal and a non-metal. Okay. Emma Hermsmeyer, NF. Covalent. Bailey, MgO. How did you know? Perfect. Okay. Natalie, CH. What? Covalent. And Next, Maya. Covalent. Now, Ryan Howard and I just kind of discussed it. If you didn't hear me saying this is very important. When it asks if something is nonpolar or polar, notice what it is attached to. It's only attached to which type? Covalent and covalent only. I'm begging you now, please do not ever list something as polar ionic or nonpolar ionic. That does not exist. That is not real. Polar and nonpolar are only associated with covalent. Okay? Yes, ma'am. All right, so you B. So let's talk about B. Phosphorus. Is it to the right of the stair step or left of the stair step? You with me now? Cool. All right. So now we need to go in and label it polar or non-polar. So let's look at the first two. So Lauren, I was kind of talking to you about this. What makes one atom stronger than the other? Based on what value? What thing? That big long word. Electronegativity. So if we look at two H's, Lauren, which one is stronger? Which H? Neither. So that means they're going to be shared how? Equally, which makes it what? Non-polar. Very good. So that's how you can tell. Okay? Ryan Howard, we've got P and Cl. First of all, of the two, is one of them stronger than the other? Which one, Ryan Howard? Cl. How do you know that Cl is stronger? It's closer to fluorine. Okay? In the math, the numbers would actually prove it. So since one is stronger than the other, what does that make this? Polar. Very good. Jamila, F2. Which F is stronger? Neither. So what does that make it? Non-polar. Yes, ma'am. Yes, whichever one is closer to fluorine is going to be stronger. Now, let me, before you go any farther, let me ask you. Let me tell you this. There are some exceptions. Okay? Remember when y'all did that sheet and it had the range, and when you subtracted the differences, wherever it fell, that's what we're doing. It's basically just an assumption, not an actual calculation. And so that's why this has it down here. Non-polar covalent has a difference of 0.0 and to 0.3. If you knew the numbers, you can actually calculate it. But we're going on just periodic trends and periodic trends only, okay? Okay. Thank you. Guys, let me pause this real quick. Okay. Johnny, NF. Between N and F, who is stronger? This is an easy one. F. So what does that tell you about this molecule? It is polar. Okay. Now, trick question, Robert. Is MgO polar or non-polar? It's ionic. What do we know about ionic? It can't be either one of them. Okay. All right. Camille, C or H? Who's stronger? Who's closer to fluorine? C. So this is going to be polar or non-polar? Polar. Very good. Okay. Okay. So this is, again, we're going based off assumptions and assumptions only. Remember when y'all took the differences and subtracted them? This is really the true way of doing it. Now, don't please stop. This is the true, actual, real way to do it, but we're going based off of just what it looks like. There could be some exceptions found in there, okay? Yes, sir. Okay, that's a good question. Now, I know this because I've been there all over, that O is 3.5. So, I know this because I've done this. O is 3.5, Cl is 3.0. Well, 3.5 minus 3.0 is 0.5. So if you look at this, 0.0 to 0.3 is non-polar. But if it's 0.4 to 1.7, it's 0.5 will fall in this range, right? So it would technically be polar based on the calculation alone. Now obviously, I'm not making you memorize those numbers. I would do this just based on the assumption that you could figure out that. So there are some weird strange ones that you could calculate that will actually fall in non-polar that are different, but it's rare. Okay, so if it is different, I'm just going to go ahead and go with the fact that it is polar simply because they're different. But just bear in mind that there could be some weird, strange attempts. Right. All right, and the last one. Marquise, HCl, who's stronger? Cl, and so what would the difference be? Polar. Now, I know that chlorine is 3.0 and hydrogen is 2.1. So what's the difference there? 0.9, right? So where would that fall?
that would fall under polar. So again, the math proves it, and I just happen to have those numbers memorized because I've done this enough. All right, so if you want to scroll down to the second page and also look at this. So this is where Vesper is really going to come into play. Yes, ma'am. I've done it so many times. I just haven't memorized. But well, remember, I gave y'all one of those worksheets actually had the numbers for every element on it. But you can just subtract it. Take whatever each number is and subtract it. Through years and years and years of experimentation and research. It's the electronegativity value. That's Linus Pauling is the person who created all those numbers. And obviously they've been adjusted over the years. But, okay. So, now, everything you need to know about Vesper is going to be contained in this sheet. Now, if you want to write it under this, it may be a good idea to understand what Vesper stands for. Hint, hint, maybe a test question. So Vesper stands for valence shell. That's the VS. We'll talk about it piece by piece. Valence shell. Now, where is the valence shell? It's the outer ring. Now, the valence shell is what does the bonding. So it's actually the electrons are going to be moving back and forth. So valence shell. EP is electron, what else come in? Pairs, electron pair. Okay? So it's those outer electrons and the pairs, electron pair, and what do electrons do from each other? Repel. So this is repulsion. Valence, shell, electron, pair, repulsion. Vesper. Not Vesifer, Vesper. I understand, but we're going to call it Vesper. So here's the deal. Here's what Vesper tells us. Every molecule has a shape. But here's the problem with that. Every shape is dependent upon how the atoms and electrons are going to fit around each other. Because certain atoms fit certain ways and certain electrons make it change the shape. So whenever I show you this molecule, right? We've been looking at this one for a really, really long time. So here's what I want you to do. See if you can use it. You can flip over it, maybe on the front, maybe on the back. And don't say it out loud. When you figure it out, just raise your hand. What is the name of this shape based on this particular sheet? Just see if you can, don't say it out loud. The name of this shape based on this sheet. Baker, what you got? It is tetrahedral. Very good. So everybody on the front, we're at the very bottom, it says tetrahedral. Now, here's the problem. Whenever you see me draw this molecule, you know, we used to start off drawing it like this. And everybody was cool with that, and everybody was great with that, because I always told you that atoms want to get really close and really far from each other. Really far. And this is perfect. But the problem with this drawing is, what type of dimension am I drawing it in? Two-dimension. Molecules are flat. They're not two-dimensional structures. They're three-dimensional. So what we have to do is we have to account for that third dimension. Now, every year I get the same argument from every student. On the sheet that you're looking at, what format is it drawn in? The left one. It's incorrect. You need to know that it needs to be adjusted for this. Okay? I probably should have whited it out by now and fixed and corrected it, but I haven't. So maybe I'll do that in the future, but I just have not done that yet. But this is the correct structure. We'll talk about those things. So whenever we get to start drawing different molecules, you will have to recognize that this has what kind of shape? Tetrahedral. Okay? And I'll ask you, what is the name of the shape of that molecule? And you'll have to say tetrahedral. Not only will you have to know the name of the shape, what is the bond angle of this molecule? Bond angle. 109.5. Now, here's the way you can measure this. No matter what way you turn this thing, are all of the sticks the same distance apart? Sure. So let's just kind of hold it from here. If I measure from red atom to red atom, would you agree, again, if this was perfect, that it would be 109 degrees apart? Yes. How do you know that it's more than 90? obtuse. It's larger than a what angle? It's larger than a right angle, okay? So it's going to be a little more than a right angle. And so this is a tetrahedron. Now, the other one that we always draw, and you've seen me draw this 100 times by this point. Okay? Now, matter of fact, check. Let's do this. When you find the name of this shape, again, please raise your hand. There's a, did you see tetrahedron? That's the name of the shape of this molecule. That molecule drawn. Okay? Emma Rizzi, what's the name of that shape? Hey, we still got over 10 minutes left. Okay, we still got over 7 minutes left. That's fine, but I'm still going. Doesn't matter. Okay, Marquise, what is it? It's bent. Now, here's the deal. Find the one that's bent. Look. How can I make this thing in my hand look like that thing on the board? Take one, all right? What's wrong? I need to take another one out. So when I take another one out, now, what can I do on the board that I can't do with this thing in my hand? I can't represent the electron pairs. Okay? But when you look at this, is that very similar? Yes. Okay? But here's what's happening. This thing is going to represent a bent molecule. Now, let me ask you something. Find the sheet. What's the bond angle of this thing? 105. Now let me ask you, this is an easy geometry question. Did they measure around the top of this molecule or around the bottom? How do you know it's the bottom? Very good. We know that a lateral line or a horizontal line is 180. Well, this is definitely more than 180. So here's what they do. When they measure these things, they measure them with the least bond angle possible. And again, this is going to be the closest thing they can possibly measure of those two atoms, which is 105 degrees. So, before you left last Friday, I got you to draw, and I think I got you to draw, correct me if I'm wrong. Is that what I got you to draw? Okay. Now, when you drew this is what it looked like. Now again, some of you have your F's a little different than how I have it. So here's what I want you to do. See if you can find the name of the shape of this thing. Hang on a second, Natalie. See if you can find it. All right, Natalie, you're the first one. What is it? Trigonal bipyramidal. Okay, Anijah. This is the weird one, and I'm going to go ahead and tell you. You will never see me ask you this question in a test format, but it's good to know. What are the bond angles for this one? Okay, so there's two of them. We're not going to get into why, how, or the way it works, but just know that that's how this structure is designed. Okay? So whenever we start drawing these, probably on Friday, because I won't see most of you tomorrow, being able to determine the exact shape based on the drawing is going to be very important. We'll also get into hybridization, and I promise you, hybridization used to be the hardest thing I could ever teach. Now, it is the easiest thing I teach. It's the first thing I teach, and it's the easiest thing I teach, okay? So make sure your iPad and the storage ready to go on Friday, because we got to flip it on.